In an earlier video, I introduced you to the mass flow rate for a flowing fluid. Here's the idea. Let's say we have a pipe with cross-sectional area A fluid with density rho is flowing through the pipe, and the flow speed is V. The mass flow rate would be the rate at which fluid mass flows from one side of a marked cross-section to the other side of that marked cross-section. We saw that the mass flow rate is given by the density of the fluid times the cross-sectional area of the pipe times the flow speed. In this video, we want to look at what happens to the flow when there is a change in the cross-sectional area of the pipe so that the pipe gets wider or narrower. For example, let's look at this figure here. In this figure, I have fluid flowing from left to right through a wide portion of the pipe, but then the pipe constricts and the fluid must continue flowing through the narrow part of the pipe. We could ask, for example, how does the flow speed change as the fluid flows from the wider part into the narrower part? There are actually quite a few things that can happen in a situation like this. So in order to get to some answers, we need to start making some assumptions. The first assumption we will use is the assumption of steady flow. The assumption of steady flow means that the fluid properties at a particular point in the flow do not change with time. So for example, let's say that I'm looking at this particular point right here, and at this particular point, I measure the flow speed, the density, the area, the temperature, whatever. If the flow is steady, I can measure all of those properties and then come back a little bit later and find that all of those properties are still the same. For example, let's say I come and look at this point right here and find that the flow velocity right at this point is rightward at 10 meters per second. If the flow is steady, I could turn away for a few seconds and then look back at this point, and I would again find that the flow velocity is 10 meters per second to the right. So let's assume that the assumption of steady flow applies to the flow illustrated in the figure. Now, I claim that if the flow depicted in the figure here is an example of steady flow, then the rate at which fluid mass enters on the left side must equal the rate at which fluid mass leaves on the right side. So using our notation for mass flow rate, that mass flow rate equals delta M over delta T, we can say that if we have steady flow, then delta M over delta T measured on the left side equals delta M over delta T measured on the right side. Now we can ask, why does the assumption of steady flow mean that the rate of fluid mass entering must equal the rate of fluid mass leaving? Let's suppose, for example, that we had 3 kilograms per second of fluid mass entering over here and 2 kilograms per second of fluid mass leaving over here. If I had 3 kilograms per second entering here and 2 kilograms per second leaving here, what happened to that 1 kilogram per second that did not leave? Well, that 1 kilogram per second that did not leave must have accumulated somewhere in the interior here. And if that 1 kilogram per second was accumulating somewhere in the interior here, that would mean that the density increased. If the density did increase, that would mean that the flow is not steady. So in order for our flow to be steady, the rate at which fluid mass enters on the left must equal the rate at which fluid mass leaves on the right. So now let's take this equation here and substitute in the values of density, area, and flow speed on the two sides of the flow. So on the left side, we have density 1, area 1, flow speed 1. And on the right side, we have density 2, area 2, flow speed 2. Now, in addition to the assumption of steady flow, we're going to assume that the flow is incompressible. The assumption of incompressible flow basically says that the density is the same everywhere throughout the flow. So if the flow depicted in this figure is incompressible, then the density on the left, rho 1, must equal the density on the right, rho 2. So the assumption of incompressible flow means for our scenario that rho 1 equals rho 2. Now, if rho 1 equals rho 2, we can come back to here and cancel the densities between the two sides. And canceling the densities between the two sides, we get area 1 times flow speed 1 equals area 2 times flow speed 2. This equation is referred to in introductory textbooks as the continuity equation. In reality, this is just a special case of the real continuity equation that some of you may learn later on if you continue studying fluid mechanics. But for the purposes of this class, we'll go ahead and call this the continuity equation. In the next video, we're going to do a simple example problem to practice using this continuity equation.